Hey everyone, so we're gonna do something very similar we did last time. Same thing, we're gonna have questions. You can look at the questions, download like the whole worksheet, looking on Canvas. So here's the very first question. So pause the video, work cell phone, go in a second. All right, so we have an object that is experiencing constant acceleration. They want us to figure out what that constant acceleration is. What we're gonna end up doing is essentially doing the change in velocity in a certain amount of time. So what we're gonna do is pick 2 points. Doesn't really matter which one. And we're gonna use the equation v equals v naught plus at. So let's do 8.5 equals 4 plus the acceleration. And then we're going to have to take the difference in the time because, this 4 is our initial, which started at 3, and we go to 6. So that's a difference of 3. So we end up subtracting this over. We got 4.5 divided by 3 equals the acceleration. So we should end up with 1.5 as our answer. All right. All right. Here's the next question. Pause the video yourself, and we'll go in a second. All right, so this is actually very similar to the question that we kind of went over, talked about in one of the previous slides with the position versus time graphs. There's a variety of different ways that we could approach this. I'm going to show the simplest way first, and then I'll show in another example in a second. So we have two cars that are separated 400 meters apart. So one thing that you'd want to do is try to draw out a picture of what's going on. So we have car A and car B. They are 400 meters apart. We have car A traveling to the east at 30 meters per second. And then we have car B in the opposite direction going 20 meters per second. And they want us to know how much time until they cross paths. Now, the simplest way of doing this is we actually can use the average speed equation with using this speed to representing the relative speed from this. Remember we talked about this idea that we can look at a scenario of two moving objects and instead consider the relative speed of one car relative to the other. That's what we're going to do here. Instead of having one car traveling at 30 and the other car traveling at 20, what I can say is let's just look in the reference frame of car A. What would the velocity of car B be? And then look at how fast it would take for B to cover that same distance of 40. Remember that the relative speed is the difference in their velocities. So we're going to do 30 minus, and then because this velocity is in the opposite direction, it'll be negative 20, telling me that the relative velocity is going to be 50 meters per second. So 50 meters per second equals 400 meters divided by t. So cross multiply. We end up getting 8 seconds as our time. So it's going to take 8 seconds for the cars to cross paths. Now, there are other ways to do this. For example, I could also draw a graph if I want. I'm not going to show that only because it takes a bit of time. But it's going to be similar to how I did the swimming problem, where we have them at two separate parts at 40, and then we could just graph what happens. Another thing I can do is I can almost, work it through second by second and see how close these cars get together. So, for example, I'm not going to do the whole thing, but I'll just set it up. So what you can do is something like say that, okay, they're separated by 400 meters. After 1 second, car A is going to move forward 30 meters and car B is going to move forward 20 meters. And then the new distance between them is now going to be 350. And then I essentially walk it through. So after 1 second, it's 350. After 2 seconds, it's 300, so on and so on and so on. It works in some cases. It's what we consider a brute force method in that it takes a while and it doesn't really get exact numbers and really nice numbers, but it's good enough to kind of answer some of the more basic questions. But this would be the easiest way to do that. You could have also actually done something similar to what we did with the swimmer, where we come up with two equations, one for the position of object A, and say that it has a equation that would be represented like this: 30 times t, and then the position of object B could be represented as 400 minus 20 because it's going in the opposite direction times t. And then we could set them equal to each other, and we'd end up with essentially the same equation that we ended up getting with the relative speed method. Okay. Here's the next question. So pause video, work stuff, and we'll go in a second. All right. So here we have a car traveling, and we need to figure out the average acceleration of the car. So we're just going to use the acceleration equation. One thing I could do is actually get rid of a few choices. Like, for example, we know that the object is traveling to the west, and it's decreasing in speed, which means that the acceleration has to be in the opposite direction. So that means that instead of in the west, it has to be in the east. So these two can be thrown out. Then I can use my equation, v equals v naught plus at. So it goes from 30 to 23. So 23 is going to be over here. 30 is going to be over here. It's still west the entire time, so there's no sign difference. I'm going to plug in 2 for over here. So subtract the 30 over, we get -7 equals 2a. Solve it, and we end up getting 30.5 meters per second squared. All right, here's the next question. Pause video, work stuff, and we'll go in a second. All right, so they tell us that the initial speed is going to be 60 meters per second. It has a final speed of 20 meters per second. Distance, or it's doing it over a distance of 36 meters, and they want us to find the acceleration. So the only variable that they didn't give us is time. So we're going to use what I call the timeless equation. So v squared equals v naught squared plus 2a d or delta x. It really doesn't matter. So we have 20 squared equals 16 squared plus 2 times a times 36. I don't have to worry about any signs. Move things around, and I should end up getting, for this question, 2 as my acceleration. All right. Let's check out question 5. So pause the video or stuff. I'll go over in a second. All right. So we end up having an object. So this is actually another variation on the this is called the META problem. So this is another variation of it where we have one car moving, forward, and then we have another car attempting to try to move up and catch up to it. So the situation will end up looking like this. Car A is traveling at 20 meters per second, and then car B is moving in the same direction, but with a speed of 15 meters per second, and they are separated by a distance of 200 meters. This time they want us to figure out how far car A has to travel in order to catch up. So we're going to start off the same way. So I'm going to just do the simple method of saying, well, we're going to do the average speed equation with the average speed this time being the relative speed between these. Because these are now going in the same direction, the relative velocity is just going to be 20 minus 15, which is just 5. So 5 equals 200 divided by t. So when we do 200 divided by 5, we end up getting that the time is equal to 40 seconds. Obviously, that's not my answer yet, so I'm actually going to go back, and I'm just going to look at car A. How far does car A actually travel in order to catch up to car B? So using the same equation, so I'm doing v bar equals d over t, but this time it is strictly car A's. So we do 20 meters per second equals the distance that A travels times by 4, divided by 40. So when we multiply 40 and 20, we end up getting 800 meters as my answer. Now, one thing I do want to point out is I didn't do it here, but in these types of problems where you have multiple velocities, multiple distances, multiple times, things like that, you want to get into the habit of putting subscripts to differentiate this average v and this average v, right? So this one you might have wanted to put relative velocity. Maybe this was, the separation. and then this is VA and DA, just so that we don't get confused. When you have so many different uh, variables of the same type, it can get really confusing which one we're dealing with. So you want subscripts to help kind of organize the information. And then we can also just keep in mind that these two times are the same, which is why I don't put any subscript on it. Right? Here's the next one. Pause video, it'll work itself, and we'll go over in a second. All right. So for this question, they tell us the initial speed of an object. So they tell us V naught. They tell us the acceleration. They tell us the time, and they want us to figure out the distance that the object travels in that time. So I'm going to use the annoying x equation, which is x naught v naught t plus 1/2 at squared. We're going to say that the initial position it was at is 0, because we're trying to figure out how far it actually traveled. So, we're looking for its final position. The velocity, the initial velocity we said was 12. The time is 3 seconds. I'm dropping a lot of subscripts because this one's a little bit longer, and I don't know if I can fit everything when using a mouse. So we end up getting this equation. We plug our numbers in. We have 36 here, and then we have 9. So we end up getting 45. All right. Here's the next one. Pause the video, work itself. I'll go over in a second. All right. So we are told how far the object travels. So I'm going to say this is the final position at 12 meters. We know the time. We know that it starts from rest, which is my initial velocity, and we're looking for the acceleration. So I'm going to use the annoying x equation. So x naught plus v naught t plus 1/2 at squared. We're going to plug our numbers in. So we have 12. The x naught and v naught are all 0. So I'm just going to drop them. I'm not even going to put in zeros for them. And we're going to plug in 4 for the time. That 4 is being squared. So this ends up being 24 equals 16a. Plug the numbers in, move things around, and we end up getting 1.5 for the acceleration. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so once again, we've seen this question up here again. Yes, this is a repeat question. It pops up a lot in a variety of different ways on the regions. So I really like this question. Here, so we have, it's the similar thing. The object goes from one end to the other 3 times, yada, yada, it tells time. But this is actually, I kind of already answered this question before. This time they're asking for the average velocity. Well, if the person starts here, goes to one end, and then comes back, and then does that 3 times, well, it doesn't matter how many times he does it. He keeps returning back to the same initial position. So velocity, the average velocity, remember, is the displacement over time. And the displacement in this case is 0. So 0 divided by 60 is obviously going to be 0 meters per second. All right. Here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so here we want to figure out, they tell us that the car starts from rest, goes to a final speed of 15 meters per second over a distance of 100 meters, and they want us to figure out what the acceleration is. So again, no time, therefore I'm going to use the timeless equation. V squared equals v naught squared plus 2a delta x. We have 15 squared, 0 squared, 2a times 100. So we're going to plug that into our calculator, solve, move some things around, and you should end up getting 1.1 as your final answer. All right. When you go do this, this should be 225 equals 200. Right. And the last question, pause the video, work itself, and we'll go over in a second. All right, so here they tell us that a rocket initially starts off at at rest with an initial velocity of 0. It has an acceleration of 20 meters per second squared, and they want us to figure out the time it takes to cover a distance of 9,000 meters. So this is going to be the annoying x equation. So x equals x naught plus v naught t plus 1 half at squared. So we're going to 9,000 meters. Again, these two terms drop out, so this is all just going to be 0. So 1 half of 20 times t squared. So 1 half of 20 is just 10. So when I divide this, it just drops out one of those zeros. So we get 900 equals t squared, square root, both sides. And you should end up with 30 seconds as your final answer. And that's it. So if you have any